Hi once again. We just seen what's going to be the Kirchhoff current voltage law equations in frequency domain, that frame. Now we came to definition relation of the elements in frequency domain. So we're going to divide the elements in three groups. One of them is the resistive elements group and inductor and capacitor. So let's go inside resistive elements. Resistor definition relation, we know that in time domain is equal to this, while R is the resistance of a resistor and this resistance value is positive real number. Since we know that the elements current and voltages is sinusoidal functions in time in frequency domain, so we can write these sinusoidal functions in terms of the phasors, while the phasors is this. So that Vt and It are going to be the sinusoidal functions. We can represent these sinusoidal functions as this, Vt and It. So if you remove that R inside here, it becomes this. Inside of the real parts should be equal. You end up with this. If you divide both sides with the a to the power j omega t, which is different from 0, then you end up with this. What is the interpretation of this is quite easy. The time domain definition relation of a resistor becomes true in frequency domain if you replace voltage and currents with their phasors. So phasor of the resistance voltage is equal R times resistor's current phasor. From here I can say that since R is the positive real number, phase difference between voltage and current is going to be the same. So that means there is no shifting between voltage and current for a resistor. That's why the maximum values happens at the same time. There is no shifting between those voltage and current. Because of that relation, since that R is positive real number, that means this, if you consider this is a complex number, imaginary part of it is equal to 0. So this is the time domain resistor. So if we transfer it the j omega frequency domain, it becomes true for the phasors. So this is phasor of voltage and this is phasor of current, and the relation between those two phasors is equal to this. Similarly, the definition relation similar to this resistor definition relation is the dependent source definition relations. The only difference is in the resistor definition relation that V and I belongs to the same element, but in the definition relation of the dependent sources, one of the variables depends on this dependent source, but the other variable depends to another element. For example, this variable here is related with the dependent sources, but that Ix here is not related to the dependent sources, but it's related to another element. But the format of these definition relation is the same as this format. So if we do the same operation that we have done here, we end up with the right hand side equations. So this is time domain definition relations for the dependent sources. In here, frequency domain definition relations of these dependent sources. What has changed? You change all the variables in these definition relations with their phasors. So phasor of current controlled voltage source voltage is equal alpha times X element currents phasor. So the format all the same. So the conclusion, resistor and dependent sources definition relations are also true for phasors. So when you say that this is true for the phasors, because the relation is the same, isn't it? This relation and this relation as format. But it is true for phasors. In here, it is true for the element voltage and current. Uh, so all the elements we have seen here are the resistive elements. So what is left? Non-resistive elements. That means energy stored elements. That means inductors and capacitors. What's going to be the definition relation of those elements? Let's examine those as well. Inductor's definition relation is time in time domain is equal to this. Since we know that all the elements, current and voltages are going to be sinusoidal functions in frequency domain, if we are dealing with the particular solution only, so sinusoidal functions these are, so we can represent the sinusoidal functions in this form, which includes the phasor in it. That is the phasor. E to the power j omega t, real part of it gives you this sinusoidal function. So if we replace these sinusoidal functions in terms of phasors here, it's going to be like that. It's not going to be like that. Let me say, so real part of inductor is going to be this. So in this here definition relation, we've got to take the derivative of the current with respect to time. If we do this operation here, you end up with this. So derivative of this, j omega times I e to the power j omega t. So if we remove that all inside and then put the inside real parts are equal, then you end up with this. How are you going to read this? Is easy. That V is the inductor's voltage phasor, that I is inductor current phasor, and the coefficient that inductor current phasor is j omega L. If we compare this coefficient with this coefficient here, that L is the same, the derivative has been changed with j omega. So that means the derivative disappears. That is the critical point, saying that we are not going to end up with ordinary differential equations because there is no derivative included in the frequency domain. Okay, that's the critical point. So derivative has been changed with j omega. Another interesting conclusion that we can get out of this is that omega is the source frequency. We know that the source frequency is also all the particular solution sinusoidal functions frequency as well. So that means omega is everywhere. We already know that in the particular solution, the amplitude depends on source frequency, angle also depends on the source frequency, and the derivative operation also includes the source frequency. That's why we call all this frequency domain. So if you compare now those two phasors, if you write these phasors in polar format, it becomes this. This equation becomes this. We replace that j with a to the power j pi over 2, 90 degree that is. If you use the Euler formula, this gives us that j. So if you make a relation between these phases here, the phase difference between voltage and current for an inductor is equal to 90 degree. So that means inductor current's phasor plus 90 degree gives me inductor voltage phasor. So when you add plus means shift left. So if you shift left the voltage phasor, voltage current, voltage angle, you get the current angle. So if you see here, the voltage phasor phase and the current phase difference is 90 degree here. So that means this been shifted right, or this been shifted left. That was not true for the resistor. In the resistor we said the phase difference, there's no phase difference for the resistor between the voltage and current of the resistor phasor. Therefore the maximum values were the same time value. But in here the maximum value of the current and voltage are not on the same line. Okay. So the next element is the capacitor. Capacitor is here. Definition relation given here in time domain. So since the current and voltages of the capacitor is for the particular solutions, they are going to be the sinusoidal function, we can replace those functions with their phasors form. So here you are, phasor of the current, power e to, multiplied e to the power j omega t, real part of it gives you ICT. Similarly, VCT is equal to this. So we are going to take the derivative of the voltage, so we're going to take the derivative of this. If you take the derivative of it, you end up with this, and then if you replace that C inside and do the operation that we have done for the inductor previously, you end up with this. So if you write it V equal to 1 over j omega Ci. So how we are going to read it? Definition relation of a capacitor in time domain becomes this in frequency domain in terms of phasors. That V is the capacitor voltage phasor, that I here is the capacitor current phasor. The relation between those two phasors is this. So that is also the definition relation. So if you write all these phasors in terms of particular format, so you end up with voltage and current phase difference of a capacitor is minus 90 degree. When it is minus 90 degree, that means capacitor voltage phase is 90 degree right shifted to current phase. There is a phase difference between voltage and current. In the capacitor, direction is the opposite of the inductor. So once again, what we are saying here, in this definition relation, we've got the derivative, that derivative disappears. In the definition relation in frequency domain, that means we are going to get rid of that ordinary differential equations and up with linear algebraic equations. These linear algebraic equations are going to have complex number because of that j here. So that is the end of this video explaining these definition relations in frequency domain. We have seen that we are not going to see the differential equations but algebraic equations with complex number coefficients. So the next is going to be the new terminology that we are going to introduce. So let's finish now.